solubility. Please remember that if it has small solubility, it means it is preferred in the form of precipitate than dissolved in the solution. And we hope that we can have a certain form of a substance that can weigh, because what we will calculate is the weight of the sample. So we have to get a certain form of the analyte that we can weigh. And like what we have talked, that excess R added will added to the solution to suppress the solubility of the precipitate. And the example is also familiar. As an example is calcium and oxalate to become calcium oxalate, and then it will combust or fire to get calcium oxide and evolve the carbon dioxide and carbon monoxide. So the one that we will weigh is calcium oxide. So this is advantages of the gravimetric analysis. It is accurate and precise. So it is more accurate, and even it's more accurate and more precise than the volumetric analysis. And any sources of errors or any possible sources of errors can be checked. Yeah, and then it is an absolute method and relatively inexpensive. So this is accurate and precise like this. Precise here, but not accurate is like this. And not accurate and not precise is like this. Yeah, so gravimetric analysis is accurate and precise method. And the disadvantage of gravimetric analysis, there are potential problems with gravimetric analysis that we must avoid to get good results. Later, we will talk about any potential problems encountered in gravimetric analysis. So that we have to do the proper lab technique. We have to be careful. So that's why it's a little bit time consuming. Yeah, it's time consuming, and we have to prepare clean glassware, and we have to accurate way so that it is necessary to prepare an accurate analytical balance. And there are some co-precipitation. It's also a problem in the gravimetric analysis. So this is like a one of the disadvantage of gravimetric analysis. This is some commonly employed gravimetric analysis. This is the substance that we want to analyze. This is the precipitate that form. This is the precipitate that we have to wait. And this is some interference or some potential impurities that accompany this gravimetric analysis. So we have several here. Probably you can read by yourself later. And at least there are two types of gravimetric analysis. The first one is precipitation, and the second one is volatilization. In the precipitation types, the analyte must first be converted to solid or precipitate by precipitation with an appropriate reagent. Then the precipitates that form will be filtered, washed, and purified if necessary, and weighed, so that we can have the quantity of the precipitate, and then we can convert so that we can get the quantity of the analyte. And the second one is volatilization. So it's based on the volatilization method. In this method, the analyte or its decomposition products are volatilized or dry, and then collect and weigh, or alternatively, the mass of the volatilized product is determined indirectly by the loss of mass of the sample. This is the example for precipitation. This is like we just previously learned that calcium could be reacted with the oxalate to form calcium oxalate, and then it will ignite so that it will become calcium oxide and release carbon dioxide and carbon monoxide. So the precipitate that we get, this is the calcium oxide we weigh, so that the calcium oxide is determined. And then in this method, we also can find the quantity of calcium in the sample. And this is example of volatilization. The analyte or its decomposition products are volatilized at a suitable temperature, and the volatile product is then collected and weighed. And then the mass of the product is indirectly determined from the loss of the sample of the mass. For example, here, water in the form of hydrous form of inorganic. For example, if we have this the material that I use when I pursue my PhD, RuO2 H2O. So this hydrous form, and we want to make it as anhydrous form or anhydrate, become RuO2. So we have to separate from H2O by volatilization, so that we have the anhydrate or anhydrous form of RuO2. So in this case, water can be separated from most inorganic compounds by ignition, so that the evolved water can be absorbed on any of the several solid desiccants. And then we can measure the weight loss as the water content in the material. So we can find the value of X here from the weight difference of the sample before and after ignition. So this is like the example. This is the copper sulfate of 5X2O. So this is in the form of hydrous form or hydrate. Sometimes we call it hydrate. And then we can heat it in a Bunsen burner flame, so that the blue crystals of copper 2 sulfate become the white powder, because it becomes the anhydrous copper 2 sulfate, copper CuSO4, and release water 5H2O. And we can use the change in the mass to determine the number of water molecules per formula in the unit sample. So we can find the value of mole of water here, or the mass of water in the sample, or even the mass percentage of hydrated compound in the mixture. So this is an example, one example of the gravimetric analysis using the volatilization method. And this is the simple one. Actually, there are some other technique to perform the volatilization method. So the simple one is only by ignite using the Bunsen burner, and we place the sample here in the crucible, and so that the water or the volatile matter will release from the cap here. So I feel much lighter now that they are gone here. So some volatile matter, or in this case is water, will evolve because of the heating process, so that we can compare the weight of the sample before and after ignition process. Here we have the criteria for successful gravimetric analysis. So for a successful determination in gravimetric analysis, we should follow some criteria here. The first one, that the desired substance must be completely precipitated. Yeah. So in this case, the precipitate of such low solubility that losses from the dissolution are negligible. So we have, if it has low solubility, then the part of the precipitate that dissolve in the solution could be negligible. So to increase the or to decrease the solubility, we can add the ion, so that it will have the common ion effect that will decrease the solubility of the precipitate, like what we have already talked previously. So for example, like the Ag could be precipitated by the addition of Cl minus. And after it formed the AgCl, we also can further add the Cl minus so that we will give the ion and it will decrease the solubility of AgCl. And we can add the we can force the reaction to proceed towards the right side or towards the product side. And then the second one, the waveform of the product should be of known composition. So we have to know the composition of the product that we weigh. And the third one, the product should be pure, so as pure as possible. Although it is very hard to get 100%, but we have to try to have nearly pure product and must be easily to filter, yeah, because it's based on the formation of precipitate. So we have to filter the precipitate after it's already formed. And it's easy to handle. For example, like the precipitate filtering, osing, drying, and weighing. Yeah, and so as a note, it is very difficult to get the product which is pure or which is free from impurities. So 100% is very difficult, but we have to try to have a nearly pure precipitate. And so what we should do to get the nearly pure precipitate is by using the careful precipitation and sufficient washing of the precipitate. So this is the unit operation in gravimetric analysis. The first one is preparation of the sample. Second one is precipitation, and then digestion, filtration and washing, drying or ignition, weighing, and then calculation. So what we will share today is about this unit operation. At least there are 7 or 8. So if we combine together, we have 7. If we separate filtration and washing, we'll have 7 unit operation. So this is like the schematic. This is the way the sample, and then we add a precipitating agent so that it will form a precipitate, and we can heat to have the formation of precipitate, and then we filter, dry, and then we before the weigh process, we should actually put in the drying oven or in the furnace or using the burner, so that we will have the dry precipitate, and then we can weigh, and after weigh we can calculate the amount or the quantity of the sample or the analyte. So the first one is solution preparation. Some form of precipitation may be required to remove the impurity, because the before we make the precipitate, sometimes the analyte also has the impurities. The condition of the solution must be kept so that the solubility of precipitate is low and it takes a filterable form. So it means that we have to get the precipitate instead of the solution. So the solubility should be as low as possible, so that it will form precipitate and it could be filtered and then dry and weigh. So some factors that we must consider. The first one is the volume of the solution during deposition, and then the range of the concentration of the precipitating agent, and the concentration of other substance, temperature, and also the pH. And this pH factor is very important because it affects the solubility of the analyzed precipitate and possible influence of other substance. For example, like calcium oxalate is insoluble in alkaline media or in a basic media, but at low pH, oxalate ions will combine with the hydrogen to form the weak acid. So like this. This in the alkaline media or in the basic media, the calcium oxalate will form precipitate. However, when it is dissolved in the low pH or in acidic media, the oxalate will combine with the hydrogen in the solution so that it will become acid, weak acid of oxalic acid. So we have to pay attention to some factors that we have mentioned previously, including the pH. And we also can add some other precipitating agent to help to form the precipitation. One of them is oxine or 8-hydroxyphenoldiene. So it can be used to precipitate some elements. In this case, the example is to precipitate Al aluminium 3+. And also about the pH, the elements can be separated selectively by controlling the pH. For example, Al3 plus can be precipitated at pH 4, while Mg2 plus requires a higher pH. However, so Al3 plus could be precipitated at pH 4. However, if we do the precipitation at pH more than 4, then if the pH is too high, then the MgOH2, magnesium hydroxide, will form. And it will also make a precipitate, and then it will cause the disturbance because we have two different precipitates. And the second, so this is the second step. The first one is the preparation of the solution. The second one is the precipitation. So the precipitate must be insoluble enough so that we can neglect the amount of the precipitate loss due to the solubility. So in this case, the precipitate that lose or dissolve in the solution must be less than 0.1 milligram, so that we can neglect the loss of the precipitate. And the second one, the precipitate whey must be pure or nearly pure and have a certain composition. And it's very difficult to fulfill, to get the pure one or the pure precipitate without any impurities. And then the third one, the precipitate should consist of large crystals so that it will be easy to filter. And suitable condition can be achieved by paying attention to the precipitation process. The first one is the supersaturation, and the nucleation, and the core growth. So supersaturation is condition when the KSP has been exceeded. So it means that the salt or any precipitates more than the salt at equilibrium. And then after it start to precipitate, then it will begin to make the nucleus or begin to form nucleation. So the nucleation is the minimum number of particles that must be combined to form the nuclei or microscopic nuclei of solid phase. The greater the degree of supersaturation, the greater the rate of nucleation. And as the rate of nucleation greater, then it will result in small particles. And if it has small particle, is formed in the form of small particle, then it will increase the absorption of impurities. So this is also a problem to get the pure precipitate. Okay, and then after nucleus form, then the third process is the core growth. So the growth of the nucleus into bigger crystal or the bigger one, bigger size. So the initial nucleus will grow into a crystal with a certain geometric shape. And when the greater the degree of supersaturation, the faster will be the crystal growth. And if the crystal growth faster, then the crystal defect will occur, and the more impurities will be trapped. So in this case, we have to control the rate of nucleation and also the rate of crystal growth, so that we will minimize the absorption of impurities and also the number of impurities that trap inside the crystal, or the formation of crystal defect. So we have to control the rate of nucleation and also the rate of crystal growth, so that we will get nearly pure precipitate. So this is like the schematic diagram. This is a homogeneous solution, and then the solubility product more than the KSP become start to have the supersaturation condition and become to form nucleation, small size of precipitate, and then it will form either in the form of coagulation or condensation, and then it's become bigger, and the crystal grows or core grows, and then after it grows, it will agglomerate each other to form bigger crystal. And all of this step is critical with the impurities trap or impurities absorption. So we have to control the nucleation growth and also the crystal growth. So this is like the schematic diagram. And what we can control is by control the von Weymern ratio, which is about the relative supersaturation. So von Weymern ratio is the ratio of the degree of supersaturation. Q minus S is the degree of supersaturation divided by S, or Q minus S per S, where S is the solubility of the precipitate at equilibrium. So we have to control Q minus S divided by S, or we call it RS, relative supersaturation. If the RS high, then it will form many small crystals. I myself, as a person who work on the nanomaterials, we prefer to have small crystal because we want to have high surface area. For example, in our research, if we use the crystal for the energy storage device, then, or as photocatalyst or as catalyst, we want to have high surface area. So in the nanomaterial, we want to have small crystal, as small as possible, yeah, but not in the form of dot, quantum dot, of course, bigger than quantum dots. Small crystals, it means that we have high surface area. However, in this case, because we talk about the gravimetric analysis, so we want to have larger crystal, as large as possible, so that it will be easier to filter and dry and weigh in the certain form. So we want to have low relative supersaturation, or low RS, so that we will have fewer but larger crystals. It means it will have low surface area. So what we have to do to get low RS, what we should do is we want to lower down lowering down the Q, and we have high S during precipitation process. So to achieve this, we have to do some steps. The first one, we have to precipitate from a dilute solution. If we precipitate from dilute solution, it means that it is at low Q, or low concentration. Q is the concentration of reagent mixture. And then add dilute precipitating reagent slowly, followed by stirring. So usually we can use the magnetic stirrer heater. So we can use steering here to lower down the Q. And then we precipitate from a hot solution, then cool down the solution to make the precipitate quantitative. It means that the remaining or the loss is less than 1 part per thousand. So that in this case, it will increase the S. And then the fourth one is we do the precipitation at the lowest possible pH, because most of the precipitate will dissolve in acidic medium. So that if it's dissolved in the acidic medium, then the precipitation rate will be slow. So we can slow down the precipitation process, because we don't want to have the high rate of the nucleation process or crystal growth, because if the nucleation rate and crystal growth rate increase, then there will be many impurities trapped inside the crystal or inside the precipitate that we have already cut. And when a precipitation is formed, we can add little excess precipitating reagent to minimize solubility. So this is like the common ion effect. And we can check whether the precipitation has already complete or not by drop a small amount of precipitating reagent that we add to the clear solution. If there is no more precipitate form, so if the solution is still clear, it means the precipitation is complete. So we can stop the precipitation. So this is the diagram. It's the formation. This is the ion in the solution. The first one, solution, when it is like the cloudy, then the size is around 10 to 8 centimeters. And then if it's become to form the nucleus, or it's form the colloid particle, the size will be around 10 to minus 7 to 10 minus 4 centimeters. And then it will become precipitate and will go down at the bottom of the glass when the size of the particle is more than 10 to minus 4 centimeter. So in this case, we will have the precipitate. So this is the particle size, colloidal suspension. This is the range of the particle size. Factors that determine the particle size of precipitate: precipitate solubility, temperature, reactant concentration, rate at which reactants are mixed. And then this is the relative supersaturation, or RS. RS equal to Q minus S divided by S. We have already talk about this, and the particle size is proportional to 1 over RS. So if RS high, then the precipitate size will become low or small. It will form colloidal, and if the RS small, then we will have the precipitate size increase, and we will get the crystalline solid. So this one that this is our goal, to have the crystalline solid with certain form and easy to filter, dry and weigh. This is the graph, the ion and precipitating reagent. It's many. This is the precipitate that get and weigh, and this is the temperature of drying or ignition. You can probably read by yourself. We have many here. I just skip. And then this is supersaturation and nucleation. If we have high RS, then it will increase the nucleation. We will have many small crystals, so in the form of colloidal, and high surface area, of course, because if we have small crystal, then we will have high surface area. And if we have small crystal, then it will have more absorption of impurities. And if many impurities, then it will be difficult to wash and filter. And if we control so that it will have low relative supersaturation or low RS, then we will have less nucleation. We will have only fewer larger crystals in the form of crystalline. So that as a consequence, because it has a larger crystal size, then the surface area will be low. And then if the surface area low, then only small amount or less absorption of impurities. So what we want to do is to get the crystalline form, the larger crystal, but with only few, so that we will have only small amount of the absorption of the impurities. So this is our goal. So we have to lower down the relative supersaturation as possible. Now the third process is the digestion. What time is it? 15 minutes left. Okay, precipitate digestion. So if a precipitate is allowed to remain in the mother liquor, then large crystal will grow from small crystals. We call it Oswald digestion or Oswald ripening. So here you can see in the figure number 1. So this is HCl, small of HCl, only small size, and it's easy to dissolve in the solution. Ag plus release, and also it come back, release and come back like that in equilibrium. Then it will, if it combine with other, it will become bigger. And if the bigger one, it will combine with other bigger size of particles, so it will become bigger one, even bigger. And what we get is the larger crystal. What we call the process is the Oswald digestion or Oswald ripening. So small particles then dissolve and reprecipitate. So dissolve, reprecipitate, go and back in the larger crystal. On the other hand, the single particles agglomerate to share a layer of ions which have opposite charges, and the agglomerated particles are finally fused together by forming a link bridge. This process, of course, will reduce the surface area. And if the surface area reduced, then crystal defects tend to disappear, and also the adsorbed and trapped impurities tend to redissolve in the solvent. And this digestion process tends to do at high temperature to speed up the process. Or we also can do at the room temperature. And the digestion will increase purity and ability so that we will get a filterable precipitate. So this precipitation is important. So many precipitates do not provide a satisfactory Von-Neumann ratio, especially those that are very insoluble. So that is not possible to produce crystalline precipitate. But the initial will be in the form of colloid or small particles with large number. Colloid particles are very small in the size of 1 to 100 micrometer. And because of small size, then it will have a large surface area to mass ratio. So when a precipitate is formed like this, for example, HCl is it's easy to use as an example. Then it will, this is HCl, 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 it will have a pattern. And because plus minus, so this one will be neutral. The electronic charge will be neutral because Ag plus and Cl minus is already balanced. However, if there is excess solution, for example, like Cl minus will be adsorbed at the surface, yeah, here, and it will form what we call primary layer. So this is the primary layer, Cl minus, and thus because this is minus, so this is not neutral. because it's not neutral, it will try to attract ions that has the opposite charges to form the second layer, so that the particles become neutrals and begins to form larger particles. So this is the primary adsorptive layers. When excess of Cl- added to the precipitate, and then because it's not neutral, it will attract other ions in the solution to form the second layer, so that the particle will become neutral electrically. It will neutral and begins to form larger particles. However, when the coagulated particles are filtered, the primary and secondary layers will be weak, so that the particles will return to the colloid forms. And this process, we call it as peptization. So when washed and filtered, the primary and secondary layer will evolve. However, when washed with water, the second layer bonds will be weak, so that the particles will return to the colloid form. So to strengthen the bonds, because we use the water, the second layer will be weak. So to strengthen the bonds of the secondary layer, and to help in the formation of coagulation, so it is important to add electrolytes. And heating tends to decrease the adsorption and effective charge in the adsorbed layer. Thereby, it will aid the coagulation. And stirring also helps. So heating and stirring will help the formation of coagulation. Although all colloid precipitates cause difficulties in the analysis, some are even more difficult when compared to others. So actually, we don't want to have the colloid precipitate. However, there is one colloid that is more difficult than the other. So there are two types: the hydrophilic, which is like water, and hydrophobic, which hates water. The solution of hydrophilic, because this love water, is very viscous. And if it's make coagulation, we call it as gel. And the solution of hydrophobic colloids is called the salt. And the coagulation of hydrophobic colloid solution is easier than the hydrophilic solution. So compare the hydrophilic and hydrophobic colloid. The hydrophilic is more difficult to handle than the hydrophobic colloid solution. The hydrophobic colloid, the example is HCl in the form of curd like precipitate. And the example of hydrophilic colloid is hydrous ferric oxide in the form of gelatin like precipitate. So if hydrophilic colloid, if it become coagulation, we call it gel, but for hydrophobic, we call it salt. And in general, we called it lyo. Lyo means solvent or liquid. Yeah, if it's the solvent is water, we call it hydro. So we have hydrophobic, hydrophilic, but generally we call it lyophobic and lyophilic. So this is the difference between lyophobic and lyophilic colloids. So this is the schematic diagram of lyophilic colloids, because it's love water, so it's surrounded by water. This is the lyophobic colloid, because it hates water, there is no water around the colloid. So coagulation is often followed by gel formation. So this is the impurities in the precipitate. Precipitate tends to carry other substances that are normally dissolved, causing contamination. This process is called co-precipitation. So when the materials precipitate, sometimes it also carry other substance in the solution that should be dissolved. However, it also precipitate so that it will cause contamination. This process is called co-precipitation. It means together, so precipitate together. There are several ways co-precipitation occurs. The first one is occlusion or congestion. So in this way, the foreign ions trapped in the crystal that are formed. It can also occur because the solvent is trapped in the crystal defect or hole. And these conditions are difficult to remove even with washing. So if we wash, we cannot handle this situation. It's difficult to handle or difficult to remove. Digestion could be helpful, but not effective. What we can do is by dissolving and reprecipitation, so that we can remove the foreign crystal or the impurities that trap inside the crystal. And then the second one, the co-precipitation, is by mechanism of surface adsorption. This is the formation of layer of impurities on the surface of the crystal, and it's easy to remove by washing or by digestion. And the third one is post-precipitation. Post means after. And this has happened because if we let the precipitate too long with the mother liquor, so that the second substance or other substance will also precipitate. And when the two compounds have almost the same formula and crystallize in the same geometric form, they are called isomorphs. And they can replace each other to produce mixed crystals. And this process is called isomorphous replacement. For example, like K+ that can replace the NH4+ in the precipitation of magnesium ammonium phosphate. And this is very serious and difficult to handle. So post-precipitation is difficult to handle. This is occlusion or entrapment, when ions are trapped inside of the crystal. We can resolve this situation by reprecipitation. And this is mechanic entrapment. So like when rapid growth traps a pocket of solution. When the solvent can be removed, the trapped ions will remain after drying. So it will trap inside of the crystal. So occlusion and inclusion are difficult to remove. Digestion may help some, but not completely effective. So what we can do if we have this situation is by dissolving and reprecipitating. The fourth step is filtering. This is the process of filtration. This folding filter paper and that put in the funnel like this, and then moistening the paper and washing by decantation and transferring the precipitate like this. This is the glass rod. This is the beaker with the precipitate and mother liquor. This is the conical funnel, and which has already we have the filter paper here, and it will separate the precipitate and the water liquor. This is the normal or manual, and also we can use the vacuum so that it will help the filter process become faster. So we can connect with the vacuum pump. So this is some filtering media for gravimetric analysis. Many paper, goods crucible, glass crucible, porcelain crucible, aluminum crucible, and you can compare here speed filtration and convenience and many more. You can read by yourself. And this is connect with the vacuum filtration. And number 5, the step number 5 or 5-unit operation is washing the precipitate. Washing is done after filtering. Many precipitates cannot be washed with pure water because baptization, so that in this case we can use electrolyte. It is volatile at the temperature when the precipitate dry or burn, so that it will not interfere the precipitate, because the electrolyte will decompose and volatile when drying process or burning process. For example, nitric acid or ammonium nitrate can be used for the HCl precipitation. The ammonium nitrate will decompose into ammonium nitrogen and nitric acid at high temperatures. And we can stop the washing process by test the presence, for example, like HCl, the presence of Ag plus ions. We can titrate a few drops of NaCl or HCl. If there is a white precipitate of HCl, then we have to further wash the precipitate. And if there is no white precipitate occur, it means that our washing is already enough, so we can stop the washing process. Number 6 is precipitate drying or firing. So before weighing, we have to heat and or dry the precipitate to remove water and also all the volatile contents or electrolytes, which we can use when we wash the precipitate. And drying usually done at the heating temperature 110 to 120 degrees C for 1 to 2 hours. However, for the combustion, we can carry out at high temperature so that we can convert the precipitate into another form which is more suitable for weighing. For example, most metals precipitated with organic reagents or with sulfides can be burned into their oxide. So if HCl only need drying at the 100 to 130 degrees C just to remove the physically bonded water. However, if, for example, we want to convert the precipitate into other form of material so that we can easy to weigh, we can perform at higher temperature. For example, this one, calcium oxalate, we can burn at, or we can heat up at 1100 degrees C so that it become calcium oxide. Or this is Mg ammonium to become Mg2P2O7. It will we can burn or heat at 900 degrees C. So this is transferring a filter paper and precipitate from a funnel to a crucible and its subsequent ignition. So after filter, we can take out the paper, filtration paper, and then we can put into muffle furnace. Or we can directly heat up in the burner, Bunsen burner. And this one is weighing. When weigh using the same container, so if we want to weigh in the same container, for example, a crucible, we have to weigh the crucible first. So we have to know the mass of the crucible before we weigh together with the precipitate. And also, if we use the paper, the filter paper, we have to know the mass of the filter paper before we use as the filtration process. So after removing from the furnace, we can place the crucible together with the filter paper and the precipitate in a desiccator for half hour before weighing so that it will more stable. And then we have to use high precision analytical balance, example like this one, which has example like 0.001 or 0.0001. So this is have more number after the point. It means it is more precise. Yeah. So this is the various instrument used in the gravimetric analysis. So this is many like magnetic stirrer heater and many glass, and this one desicculator, or we can use desiccator also. This is crucible, glass crucible. You also can use ceramic crucible. And this is when we prepare the solution. We weigh first the solution. We have to give the name here so that it will not confuse with other sample. Give the number or any label so that we understand which one is which. Yeah, so that we can put in the glass beaker and react with the precipitating agent, stir using the also magnetic stirrer heater at certain temperature, depends on the formation of precipitate. And then we can dry. Before this we have to filter first, and then we dry, and then we can weigh. So we can use desiccator to place the crucible after drying before weigh. So it's like this. And next one, the last one is calculation. We can calculate using gravimetric factor. So the percent A, or the percent of analyte, equal to mass of gram of A divided by gram of sample times 100%. So we'll have percent of salt equal to weight of precipitate in gram divided by the sample of the sample weight, and also in gram, times the factor of gravimetric, or gravimetric factor, times 100%. So for example, if we want to find SO3, the precipitate that we weigh is barium sulfate, then the gravimetric factor will be the molecular relative or molecular weight of SO3 divided by the molecular weight of barium sulfate. If we want to find Fe3O4 and the one that weigh is Fe2O3, then because this is 2, this is 3, we can calculate, we can multiply 2 Fe3O4 divided by the molecular weight of 3 Fe2O3. So here Fe6, here Fe also 6. So it will be equal. And if we want to find Fe from Fe2O3, then because this is 1 mole, this is 2, so we multiply with 2 Fe divided by molecular weight of Fe2O3. Then if the short one, if MgO, the weight is Mg2P2O7, then because this is 1, this is 2, we multiply with 2. The numerator with 2 to MgO divided by Mg2P2O7. And here P2O5, here 2, here also 2, so we don't need to multiply with anything. Just the ratio of the molecular weight. And this is Cr2O3, Pp Cr04, this is 2, this is 1. So we have to multiply the numerator with 2. So this is example problems. We have orthophosphate PO4 3 minus is determined by weighing an, let's see, an S-ammonium phosphomolybdate is NH43 PO4 12 MOO3. So calculate the percent of P in the sample and percent P2O5 if 1.1682 gram precipitate were obtained from a 0.2711 gram sample. So percent P, this is the precipitate. precipitate. So this is the molecular weight of P. This is the molecular weight of the weight, yeah, divided by the mass of the sample is 0.2711 gram times 100%. So the molecular weight of P is 30.97. The molecular weight of this compound is 1,876.5. So here, if I times the gravimetric factor divided by the mass of sample times 100%, so that we get 7.111%. Then this is P2O5, because here P2, here only 1, so we have to multiply with 2. So we can calculate like this. This is 2 times 1,876.5 divided by the mass of sample. So we get percent P2O5 is 16.3%. Okay, and number 2. An ore is analyzed for the manganese content by converting the manganese to Mn3O4 and weighing it. If a 1.52 gram sample yields Mn3O4 weighing 0.126 gram, what should be the percentage of Mn2O3 in the sample? And what is the percentage of Mn? So here, percentage of Mn2O3, this is the mass of the weight. So the sample that weigh, this is the gravimetric factor, because this is 3 and this is 2, this is 3 and this is 2 and 3. So we have to multiply this one with 3 and this one will with 2, so that Mn will be 6, this one also 6. And divided by the mass of the sample, we can just add the value of each. So it will get 8.58%. For Mn, the sample is Mn3O4, because this is 3, so here must be multiplied with 3. So do the same mathematical calculation as the previous one. We get the percentage of Mn is 5.97%. This one. And this one, number 3, what weight of pyrite ore, impure FeS2, must be taken for analysis so that the barium sulfate precipitate weight obtained will be equal to half that of percent S in the sample. So we assume that percent S here is A, so A%. And the percent of barium sulfate will be half of A, half a percentage of S, so half A gram. Therefore, A% S equal to half A. This is the gram of barium sulfate times S divided by barium sulfate, the molecular weight of S divided by molecular weight of barium sulfate divided by the mass of the sample. So this is 1%, because this should be omitted like this. So it become 1, this is become half times the molecular weight of S, molecular weight of barium sulfate, divided by the gram of sample, so that the gram of the sample will be 6.869 gram. So this example problems is from the Carrie D. Christian. So this is from the first reference that I have already written in the previous slide. So this is from this book. If you want to find by yourself, or probably your lecturer have already given to you. So this is number 4. Mixture containing only FeCl3 and AlCl3 weigh 5.95 gram. The chlorides are converted to the hydrous oxide, then ignited to Fe2O3 and Al2O3. The oxide mixture weighs 2.62 grams. Calculate the percentage of Fe and Al in the original mixture. So the solution, there are two unknowns, so we have to have two simultaneous equations. For example, assume that X is gram of Fe and Y is the gram of Al. Then for the first equation, gram of FeCl3 plus gram of AlCl3 is equal to 5.95 gram. So this is number 1. And this is number 2 in the form of chloride and in the form of oxide. So this is number 2 and this is number 1 and this is number 2. And because the 1 mole of Fe is equal to 1 mole of FeCl3, so this is mass of Fe divided by molecular weight of Fe equal to mass of FeCl3 divided by molecular weight of FeCl3. So if we want to find the mass of FeCl3, it becomes mass of Fe times the molecular weight of FeCl3 divided by molecular weight of Fe. Mass of Fe here is X. So here, this one, X times the molecular weight of FeCl3 divided by molecular weight of Fe. And in the same way, it's like this for the LeCl3. Y times the molecular weight of AlCl3 divided by molecular weight of Al equal to this. So we can just input the value of the molecular weight each of the compound and elements. So we get the equation number 4. This is the first equation. And then for number 5, this is for oxide. We do the same thing so that we get the equation number 8. So this is the 2 equations that we have simultaneously solved. Then using equation 5 and 8, we get that X equal to 1.07 gram and Y equals 0.85 gram. So get percent Fe equal to 1.07 gram divided by 5.95 gram is equal to 18%, and percent of Al. So from the original mixture, so the original mixture is this one. Yeah, okay, 5.95 gram. So it's become 9.8%. So now it's finished, Dr. Sabiha.
Yes, I think maybe you are running time because you will attend the meeting, right?
Yeah.
Yeah, maybe we can open the questions. Maybe the student want to ask any questions.
Yeah. If they do not, they didn't sleep because it's critical times.
Yes, doctor. I need you to share your slide. Okay.
Yeah. Okay. Let me understand.
Yeah. Okay. So I open any questions. If the students you want to ask any questions.
Yeah. If I cannot answer, then Sabiha will answer for you.
Yeah, it's okay. Okay.
Anyone?
Yeah, actually, I don't give the lecture yet, so it's good for them. Yes.
Oh.
Yeah.
Because
So,
yes.
Yeah. Anyone?
Anyone who wants to ask?
No, madam.
Oh, no.
No question, madam.
No question. Okay. No, Hamiza, you have any questions?
No, madam.
Okay.
So good.
Okay.
Really? Or do you
So
sleep?
good.
Are you sleeping now? Because it's critical time.
Yeah.
So after lunch, probably
Yes,
it's
yes.
sleepy.
Actually, this time actually my lecture during this time.
So
Yes. So anyone you want to ask? Okay, maybe I can ask one question, Dr. Claire.
yeah.
So actually, in the nanometric course, you prefer the colloid or the crystal?
Pardon?
For the nanometric course.
Gravimetric.
So nanometric course, you
Oh,
prefer
nano.
colloid? Yes. You
Yeah,
prefer colloid or
yeah.
crystal?
Yeah, for the nanomaterials, because we require nano size of the material, so
Okay.
we prefer to have a small crystal so that it will have a large surface area.
Okay.
So it's
So,
like,
so in the form of meaning that you want the crystal, right?
yes.
Yes. Okay. Okay, actually one more thing, because I mean in our syllabus, we don't have the lipophysics. So what is the difference? Lipophysics and also lipophysics.
Pardon, I could not.
The difference between lipophilic and also lipophysics.
Oh, this is only a term. Lyophobic is, it means like the hydrophobic, but lyo is more general because it's because of the it lyophilic means it loves the solvent. Lyophobic it means it hits the solvent. But for
Oh,
the
okay.
hydro is more specific only for the water. Yeah, lyo is more general term.
Okay, thank you. So, any questions? Yes. So,
Yeah,
I think,
yeah. If no
yeah.
question, I will ask you.
Dr. will ask the questions. Okay.
Okay. Before we finish, I think we still have some minutes. Yeah,
Yes.
9 minutes, I think. So this is number one. What is A, B, C, D? Hello, student. Hello. We love Ipin Upin, you know. My children every day they watch Ipin Upin. So we are in the same,
Okay.
yeah, in the same universe, you know. So what is number one? What is the answer number one?
Okay. Anyone to answer? Because
Yeah.
already A, B, C, D. You can choose.
Which one? A, B, C, D.
Okay. Anyone to answer?
This is the like the ice that Ipin Upin usually ordered to Uncle Muto. Like A, B, C, D.
Yeah, you can choose the answer. The answer is already there. A, B, C, D.
Hello.
Okay.
Hello, student.
Yes, doctor.
Yes. Which one?
I think the answer is D.
Really?
D. The measurement of
She answers.
But for me, I think the answer is D.
D. Any other answer?
C.
Yeah, it should be
C.
C. Yeah, C. It should be C. The measurement of the change in the mass after removing volatile compounds from a sample. Yeah. So this is the keyword volatilization. So this is volatile. Number two, student wants to determine the amount of sodium bicarbonate in a sample using volatilization gravimetry. The student reacts the sample with dilute sulfuric acid, resulting in the reaction like that. What volatile molecule will the student measure? A, B, C, D, E. A, yes, you are correct. CO2, because this should be volatile. Number 3, a precipitate FeOH3 was contaminated with MgOH2. The best procedure to replace the precipitate is digestion, washing, reprecipitation, or ignition. A, B, C, D. Should be hello?
C.
C, yes. Okay, number 4. Colloids that contain a lot of water, then when agglomerated are referred to as
B.
D.
No. B. Gel. But Leophobic will be straw. Leophilic will be gel. A should be A. Okay. And numbers 5 and 6 here. Number 5, the process of dispersing an insoluble substance in a liquid as a colloid is referred to as A, B, C, D. Which one?
D.
B.
B, yes, B. Number 5, which one of the following which will not promote the formation of large crystal calcium oxalate? Please remember that oxalic acid is a weak acid. So which one? A, B, C, D. Will not promote the formation of large crystal. So it means that
D.
what? Pardon? A, B, C, D?
D.
D.
Yeah, should be D. Yeah, the relative RS, relative saturation, high. Okay, the last one. Which one? The strongest ions at the colloid particles before the equivalent point. So previously we have already AgCl, right? So which one? Then A plus, Cl minus, Ag plus, CO plus, or OH minus. Should be
B.
B, yes, Cl minus. Okay, and this one we should calculate. I think it will be time consuming, and this is some example problems that you can solve. And it's from the book. I forget what it. Underwood. Underwood. Okay, I think finish Dr. Sabiha. Thank you.
Thank you very much, Dr. Diah, for your sharing. Okay. I hope this student you can on your camera. We will take the photo. Okay.
Okay.
Because some of the students, their mobile data already make it their internet very slow. Yeah.
Yeah.
Okay, some of you, if you can that on the camera, so you can. Okay. Okay, wait, Okay, you ready? Yeah, I count. Okay, 1, 2, 3. Okay, smile. Okay. I try what? Because this Google Meet, we cannot put together. Okay, wait. I try to change.
Cannot hear.
Boleh? Cuba. Siapa yang boleh buat? Cuba ambil.
Kamu nak ke?
Kalau boleh. Yes. Saya punya tak boleh. Cuba kamu buat. Mungkin saya tak tahu. Boleh? Okey, kamu kira. Nanti kamu share dalam
Siapa boleh tak tolong screenshot kan?
Saya.
okey, okey. Alright. Okey. Okey, kira.
Good. Belum.
Okey.
Dah.
Okey. Okey dah. Okey, thank you. Okay, Dr. Diah, thank you very much for today. So I hope you can share the slide, right? Because the request is like, yes.
Yes.
Okay, okay, the student, you want to say anything to Dr. Diah for the today later?
Thank you so much, Dr. for
You're welcome.
Thank you.
Nice to
Thank you, Doctor.
Okay, thank you.
Thank you, Doktor.
Ya, sama-sama.
Okay.
Okay, Aileen. Okay, doctor.
Okay, you have the meeting. Okay, thank you.
Ya.
Okay.
Assalamualaikum warahmatullahi wabarakatuh.
Waalaikumsalam.
Selamat siang.
Okay.
Thank you, Doktor.
Okay.
Bye, Dr. Sabiha. Thank you.
Okay, thank you so much, Amalia. Okay, thank you for all the students. Okay.
Yeah, you're welcome.
Okay. Right.
Bye. Assalamualaikum.
Bye. Waalaikumsalam.
Salam.
Okay, nanti you ada share. Siapa yang ambil gambar?
Saya dah share dekat dalam.
Oh. Oh, okay. Okey, terima kasih ya. Nanti kalau apa-apa nanti saya akan share nota tu di dalam grup. Okey, minta maaf lah sebab kita ambil masa lebih sikit dalam 1 jam setengah. Ada kawan-kawan kamu kata apa, dia punya mobile data pun dah bila kita buka bila kita buka komputer. Okey. Nanti minggu depan lecture kita balik kepada Microsoft Teams, right? Okey, kalau you tak ada apa-apa soalan ni, kita sampai sini je lah. Terima kasih sebab you all ada bagi kerjasama lah untuk join the program. Okey? Okey, thank you. Okay, Assalamualaikum.
Salam. Thank you,
Thank you, Doktor. Madam,
Yes.
attendance yang madam baru share tu kena isi lagi sekali
Sebab dia ada beza tu. Yang tu adalah attendance untuk saya. Sebab saya juga akan prepare certificate. Lepas tu yang satu lagi tu adalah attendance daripada ITS. So daripada ITS tu dia akan bagi certificate. Berdasarkan pada attendance tu lah. Kalau dia pelajar-pelajar akan dapat 2 certificate.
Okay.
Okay.
Terima kasih, madam.
Okay, baik.